We introduced the mean value theorem for derivatives yesterday. I want to look at an example or two with that, and then I want to show you the mean value theorem for integrals, which is similar, but obviously a little bit different. So let's look at one quick review. So here's the mean value theorem, right? What are the criteria you have to meet? Two things. The function has to be smooth, so it's continuous on the closed interval, differentiable on the open interval, and the other part of it is actually that's it for the mean value theorem. That's it for and then what it tells us is if that's true, if we have a smooth function on some interval from a to b, then there must exist at least one number c in the open interval, so between the endpoints, such that the instantaneous rate of change is equal to the average rate of change over the interval. Okay? As a picture, it looks like that, doesn't it? Right? If we've got this blue function that's smooth, so it's continuous and no sharp corners, no vertical tangents, right? Then the average rate of change is just the slope of the secant line connecting the points at x equals a and x equals b, right? So it's just going to be, f of a or f of b minus f of a rise over b minus a run. Just calculating a slope, the difference quotient. There has to be at least one place on the interval where the slope of the tangent line is equal to the slope of that secant line, maybe multiple. Okay? So again, it's an existence theorem. It tells us that if we meet the criteria, then there exists something that we can go find if we want to. Okay? So let's look at an example. How about this guy? So does the mean value theorem apply? And if so, what are the values of c that it guarantees for the function f of x equals x plus 1 over x on the interval from 1/2 to 2? Okay. Is the function smooth on that interval? Well, is it continuous? Where's the only discontinuity that this function has? It's 0, okay? But that's okay as long as the discontinuity is not in our interval. It's not, is it? Right? We're good. This function is continuous. And now, is it differentiable? I guess that's the next issue. How are we going to know if the function's differentiable? It's difficult to say by just looking at the function. What would we probably need to do here? Say it again. Find the derivative, sure. Okay, so is there a more convenient way to write this function so we don't have to use the quotient rule? Say it again. Okay, I mean, I could do x plus 1 times x to the negative 1. Then I've still got to use a product rule, right? How could I rewrite that argument of the derivative there? How could I rewrite the function in a way that I could differentiate it much more easily? Yeah, let's just split the denominator and simplify each fraction, right? So I could write that as 1 plus 1 over x. And we still see that the only place that's undefined is where I have an x on the bottom, right? So if that's the case, then what is f prime of x? What is it again? Yeah, negative 1 over x squared, isn't it? Okay. So the function, wherever the derivative function is undefined, that's where the original function is not going to be differentiable, right? So where do we have problems with our derivative? At 0, yeah, right? So our function is not differentiable at 0, which doesn't matter because 0 is not even in our domain. But every place else we're fine, aren't we? Okay? Give me 1 to 5 on that. Does that make sense? Okay. So we're good. This thing meets the criteria of the mean value theorem, right? So does it apply? Yes, it does. It applies, right? So now we've got to go find the value of C. All right, well, we just want to ask the question then, we want to find where is our derivative equal to the average rate of change, okay? So we're solving the equation, where is negative 1 over x squared equal to, what's our average rate of change going to be? You don't have to give me the final answer, but how would I calculate it? F of, okay, and what's our F of B minus F of A, right? What's our B? 2. Okay, so we're going to get F of 2 minus F of 1/2 divided by 2 minus 1/2. Okay, good. So then that gives us the equation negative 1 over x squared equals F of 2 is just going to be 1 plus 1/2, right? Okay, so 1 plus 1, or we could use this one, if we want to use this guy up here, maybe that's better. 3 over 2 minus F of 1/2. Well, that's going to give us 1/2 plus 1. Maybe this one's easier for that, isn't it? 1 plus 1 over 1/2 is just 2, right? So 1 plus 2 is 3. Okay. Divided by 2 minus 1/2. Well, that's just 3 halves. So what's that give us? 3 halves minus 3 is negative 3 halves over 3 halves is just negative 1. Okay. So we got to solve the equation negative 1 over x squared equals negative 1. What would I do? I mean, a couple ways. I could flip both sides. I could cross multiply, right? I could multiply each side by negative 1 to make those positive initially. How about? And so I end up getting the equation x squared equals 1. Everybody agree? So my solutions are then x equals plus or minus 1. Everybody buy that? No. What are the values of C that are guaranteed? Only one of those is guaranteed. Look at our interval. Only positive 1 is in our interval. Negative 1 is not. So what are the values of C that are guaranteed? We eliminate that guy and we get our solution is just C equals 1. Okay, make sense? Okay. Let's maybe look at just one more quick one. How about one like this? This time we got the function f of x equals 2 sine x plus sine 2x. Okay, first of all, is there any place where that function is going to be discontinuous? No, right? I'm just taking sines of stuff. Sine functions are continuous everywhere, right? When I take a derivative, which I have to do, so let's calculate a derivative. What am I going to get? Cool, I got just differentiate term by term. 2 times the derivative of sine x, which is just cosine x, right? So 2 cosine x. And then what's the derivative of sine 2x? Got to use chain rule. 2 cosine 2x, right? Derivative of sine hand is cosine hand times the derivative of hand is 2, right? So I get plus 2 cosine 2x. So there's my derivative. Let's calculate the average rate of change, right? So average rate of change here is going to give us, we'll just call it slope of secant line. How about this time? Slope of secant line is going to be f of pi. So if I evaluate this at pi, what's that going to give me? 2 sine pi. Sine of pi is 0. Plus sine of 2 pi is also 0. So I get 0 minus f of 0. Sine of 0 is 0, right? So I just get 0 minus 0 over pi minus 0. Everybody good with that? Okay, which is just 0, right? So we want to know, where is our derivative equal to 0? That's the equation that we're going to solve. Oh, I guess, would everybody agree that maybe you already said this, the derivative function, being as it just involves cosines, is defined everywhere, isn't it? There's no problem. So this function is clearly a smooth function, which we could have anticipated, because I'm just dealing with sine functions, and sine functions are smooth functions, aren't they? Continuous, and they have no sharp corners, no vertical tangents. They're very well behaved. Okay. The reason I want to do this one, though, is it involves solving a trig equation, and you guys, you're not great at that because you haven't done it very much. So the more practice you get, the better you're going to be, right? So how am I going to solve this equation? I want you to get to a point where you look at that and say, okay, that's the way that equation is written is not very convenient. What's inconvenient about it? Yeah, look, I've got the angles, right? I've got an x and a 2x, and they don't mix well, right? So what we want to do here is we want to be able to write that in terms of just a single type of angle. We don't want to have x's and 2x's. That makes it very difficult to find zeros of that function, right? So what are our options? And this goes back to properties of kind of the trig identities and all that good stuff, right? So this is an important one. This is the double angle formula. The one we don't need right now, but I still want to review, is sine of 2x. What is sine 2x? I guess is this the half angle formula, I guess, because I'm cutting the angle in half. What is that in terms of x's? Not remembering. I mean, I get it because you don't use it very much. So I feel like I haven't done my job. I feel like I haven't made you guys memorize this stuff enough. I probably need to do that. I keep saying I'm going to, and I just resist because I don't hate wasting time on it, but probably need to have just a little memorization thing where you guys got to memorize this dumb stuff. Okay, that one is 2 sine x cosine x. Right? Okay, so what about the cosine? Cosine 2x is equal to, kind of a weird one, cosine 2x is equal to cosine squared x minus sine squared x. But we could use the Pythagorean identities to convert cosine squared to sine squared, or sine squared to cosine squared, whichever is most convenient, right? So if we want to write this in terms of sines, I would say, okay, well then we remember that sine squared x plus cosine squared x is 1. That's our Pythagorean identity, right? So if I solve for cosine squared, that's just 1 minus sine squared, right? So 1 minus sine squared minus another sine squared would equal 1 minus 2 sine squared x. If I want to write this in terms of cosines, I'm just going to do the opposite. Sine squared would turn into 1 minus cosine squared. So I'd get cosine squared minus the quantity 1 minus cosine squared. So I end up, when I distribute the negative, I get 2 cosine squareds minus 1. Okay, so those are the identities, the important trig identities here, those half angle formulas. Which one are we definitely going to choose? Which one? I want this one, right? Because look, I've got a cosine there. I want this all in terms of the same species of trig function too. That's another thing that makes this way easier, right? So if I use that identity, then look what happens to this equation. I end up with the equation 2 cosine x plus 2 times cosine 2x which is 2 cosine squared x minus 1 equals 0. Okay, well, look at that. I could write this as a quadratic equation in cosine x, meaning in pieces of cosine x, right? If I distribute the 2 and redistribute these or rearrange these terms, I get 4 cosine squared x plus 2 cosine x minus 1 equals 0. Did I mess something up here? Oh, yeah, minus 2. You're right. Whoops. Yep, I got to distribute that too, don't I? There we go. Okay. So I could divide everything by 2, right? Divide both sides by 2. And that's going to give me 2. And I'm going to rewrite this as, I'm just going to do something a little different here. I'm going to rewrite this as cosine x quantity squared plus cosine x minus 1 equals 0. Well, look, that just looks like a quadratic equation with coefficients 2, 1, and negative 1, right? Where a, b, and c are 2, 1, and negative 1. So that factors, right? That factors. If I just forget about the fact that those are cosines, we know that that's going to factor. Like if I were doing the equation instead, let's just look at this one. What if those were just instead, that was just 2x squared plus x minus 1? Wouldn't that just factor into 2x minus 1 times x plus 1? Then that would FOIL properly, wouldn't it? Everybody see that? But we don't have x's, we have cosine x's. So this looks like 2 cosine x minus 1 times cosine x plus 1 equals 0, right? Okay, do you see the strategy here? We've done two very important things. We've written this in terms of a single type of angle, x's only, and we wrote this in terms of a single type of trig function, cosine of x, right? So now we can look at this and solve this like we would any other polynomial equation, only it's not really a polynomial because instead of the input variable being x's, they're cosine x's, right? But it still factors the same way, right? We still factor it. It factors like a quadratic because it is a quadratic form, right? Okay, give me 1 to 5 so far. Does that all make sense? Okay. Well, now that we've got this thing factored, I can just apply the zero product property, right? So what's going to be the zero of this function here? Well, we're solving this for cosine x. We're not solving this for x yet. We're just solving this for cosine x. So one solution would be that cosine x equals 1/2, right? Everybody buy that? Okay. The other possibility would be cosine x equals -1, and then we just go to the unit circle and find those places. So on the unit circle, on our domain, which is between 0 and pi, so we're only looking at this part right here, between 0 and pi, where is cosine x equal to 1/2? No. Pi over 3 would be 1, right? Because cosine is the x coordinate. So one place is going to be right there where we end up with coordinates 1/2 square root of 3 over 2. Actually, there's only one place, isn't there? It's just right there. That's it. That's the only place, right? Which is the angle that's going to be pi thirds, right? So there's one solution. X equals pi thirds on our domain, the only solution for the green equation. Now, what about the blue one? Cosine x equals -1. What's the only place where that occurs? I guess I should do this. Why don't I make that green? Where's the only place where cosine x equals -1? What were you saying, Jonathan? Okay, so what angle is that? Pi. Yeah, right there. Okay. Okay, so the other possibility is x equals pi. Okay. So do we include both of those solutions? Pi halves and pi? What do you think? Thumbs up? Okay, anybody say it's thumbs down. Only one of them gets included, but why? One's an endpoint, right? And what's the mean value theorem say? Then there exists a number c in the open interval, right? Between the endpoints. Pi is an endpoint. And so that is not one of the values of c that's guaranteed. Okay, it's incidental. Okay. So we exclude that one, and our only solution is that guy right there. So I guess we'd call that c. C equals pi thirds. Okay, make sense? Okay. All right, so what about one like this then? This is just an example of what you'll later learn as Newton's law of cooling. We'll look at this. Yeah, we'll look at this when we get to. It might be post AP test possibly, but we'll look at this. This is a log problem. We'll solve this differential equation. I don't know if these are. I got to look. I don't even know if these are on the AB test or the. Yeah, I'm not sure. They might be. Yep. Oh, we'll just look at some just random stuff. We'll slow down a bunch, and we'll just look at a couple other additional topics, just kind of getting ready for college topics. But I'll slow down. I know, and like I'll tell you what I will do for you guys, seniors. I well remember how hectic it gets right at the end for you guys. So we'll go ahead and cut ours off a little bit early. We'll do our, finish all our stuff a little bit early, right? So you got a little extra time to deal with senior stuff because I know that's real busy. Okay, so how about one like this? When an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, so like a great big water bath, that's it, like a really big swimming pool that's at 90 degrees Fahrenheit, okay? Its core temperature when we drop it in is 1500 degrees Fahrenheit. 5 hours later, the core temperature is 390 degrees Fahrenheit. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour, right? So if we were going to talk about this, like if we were going to define a function here that's going to be temperature as a function of time, is that going to meet the criteria of the mean value theorem on our domain, which is going from 0 to 5, isn't it? Right? We're starting the stopwatch when we drop it in to the water bath, and the stopwatch ends at 5 hours when the temperature is dropped to 390. Okay? So what do you think? Is it going to meet the criteria of the mean value theorem? Would this temperature function, if I were to graph temperature as a function of time, would it be continuous? What do you think? Wouldn't it have to be? How could it not be? Is it just suddenly going to instantaneously drop in no time from one temperature to another temperature? That can't happen, right? The temperature has to flow away from the object continuously. And so that could never happen, right? So it's got to be continuous. What about differentiable? Well, it's going to be differentiable too, right? Because you can't have any sharp corners there. You can't have all of a sudden, you can't have the rate of change of the temperature just instantaneous, temperature change instantaneously shift. It's going to be a property of the type of material it is. And so it's definitely, this is a physical thing. So it's going to meet the criteria of the mean value theorem, right? MVT. When would you find something that doesn't? It's hard to in the real world. Like quantum mechanics would betray that principle. Quantum mechanics, energy levels can just instantaneously jump. But otherwise, it's really difficult to find situations where you have physical processes that don't adhere to the criteria of the mean value theorem, right? They almost always will. So we meet the criteria. So then what's that tell us? That tells us that if we meet the criteria, then T prime of T, there must be a place where that equals the average rate of change, which is just the change in temperature over the change in time, right? So it's going to be 1500 degrees Fahrenheit minus 390 degrees Fahrenheit divided by 5. And that works out to be, I believe, 222, right? It's got to be. So what's that give us? 1110 divided. Yeah, so it is. It's 222. So therefore, it has to happen. There has to be at least one place where that happens. And if we look at a graph, I kind of put together a little graph of modeled this to show you what it actually would look like. If you do the integral calculus and you solve that differential equation, the red function is exactly what that cooling process would look like. Temperature is a function of time. It's logarithmic. It's actually exponential, not logarithmic, sorry. It's exponential. And so this would just be the point right here. We're measuring on this axis temperature in degrees Fahrenheit, and we're measuring on this axis time in hours. And so this would be the ordered pair 0, 1500, and this would be the ordered pair 5, 390. And there's going to be one place where the slope of the tangent line equals the slope of the secant line, and it looks like it's right. I drew that not very well, but you get the idea. Someplace kind of like right in there. That's going to be, those would be parallel. Anybody buy that? Okay. So what's kind of cool there is we can't really solve anything, but it's an existence theorem, and we can just, it just proves that, yeah, it has to happen, right? It has to happen somewhere in that interval. Okay, so next issue, the mean value theorem for integrals. So this is a little bit different. The mean value theorem for integrals is similar. It's an existence theorem. So it just shows, it tells us that what are the criteria here? If some function is continuous over an interval, okay, a to b, I don't think it needs to be differentiable. It doesn't need to be differentiable, just continuous. Then there is at least one point C and that should be, I think they made a mistake here. I'm convinced they did. This should be that. Should be in the open interval, so between the endpoints, such that the average value of the function is equal to this expression, which looks mysterious probably to you, but it's not so mysterious. If we write that as a quotient, what's that mean? Well, the integral of f of x dx from a to b means what? What's that represent? Area under the curve on our interval, right? Divided by the width of the curve. Okay, think what that means. All that means is we could reconfigure the area under the curve so it had a flat top instead of a curvy top. That's it, right? The area under this curve, this purple curve from A to B, is equal to the area under the red curve. All I did was I just redistributed that area up there in that hump into that valley, that hill into that valley. It's like I took a calculus grinder and just ground that down into rubble, and I pushed the rubble over to fill in that pit. You see my point? Okay. So we could define a new function, and what's the implication of that? Well, One interesting application of this would be if we go back to kinematics. In kinematics, I think we talked about this a little bit, but didn't go very far with it at the time. If we're looking at, instead of this being y, let's have this be velocity. This is velocity measured in meters per second, and this is going to be time measured in seconds. So the area under a velocity time graph is, what do you think it is? Think about what the units would be. The height would be measured in meters per second, and the width would be measured in, it would be a dimension measured in units of seconds. So I'm going to get meters per second times seconds, so I'm getting units of distance. Okay, it's not actually distance, it's displacement. Okay, which makes sense, doesn't it? Because then if I had a negative velocity, right, the velocity dipped below the t-axis, then that area would be negative, and that would correspond to negative displacement. Does that make sense? When the velocity is negative, like if I'm moving in my velocity is negative, I'm moving in the negative direction. So during that interval of time, my displacement should be negative, right? Because I'm traveling in the negative direction. So we're just going to add up the total displacement as a cumulative function, and we end up with net displacement then, right? If I were to move, like if I had as much positive area as negative area, that would mean that my positive displacement was canceled out by my negative displacement, and I end up right back where I started. Okay, make sense? So one example would be something like that. The area under a velocity versus time graph equals displacement. Another example would be the work stuff that we talked about the other day, right? Remember we looked at the baseball being hit, and we said if we took a force versus distance, I got force on the vertical axis and distance on the horizontal axis. Force versus distance equaled work, or the amount of energy transferred, right? So we could do something similar there. The area under a force displacement or a force distance graph is total energy, right? And that can be negative too, right? The total amount of kinetic energy we're imparting. If I am slowing something down, then I'm doing negative work on it because I'm robbing it of kinetic energy, the energy of motion, right? These specific examples, I know you guys are thinking, oh my God, we don't know about anything about physics because you're not taking physics, but you will, and you'll see this, right? I want to attach this to some kind of an example. So let's just stick to one. That's an easy one to deal with. Area under a velocity time graph is displacement. So what does this mean then? Like if I travel this purple timeline, so my velocity starts off at 10 meters per second, I'm accelerating up to some high velocity, and then I'm going to start to slow down till I get down to some low velocity, and I finish at about, 8 meters per second. Well, during that interval where my speed is changing, it's always positive velocity. So the whole time I'm accumulating positive area. So I end up with some displacement that corresponds to that integral, right? How could I end up at time A, I'm starting, and at time B, I'm ending? What would be a much simpler way for me to get to the exact same point in the exact same amount of time to have the same displacement? What does that imply in terms of my motion then? Yeah, I could also just put the cruise control on and move at constant velocity and pick the right velocity so I end up having the same displacement, right? Everybody agree? Give me 1 to 5 on that because that's pretty important. Does that make sense? Okay, so I could either have this continually changing velocity where I'm speeding up and slowing down, but after a couple seconds I end up here, or I could just walk at constant rate, end up at the same spot if I pick the right speed. Okay, well, that's the speed that is given to us by the mean value theorem for integrals, right? I'm going to pick the height of that function to be such that the areas are the same, right? Everybody get that? Okay. So then in this case, if it just happens to be that that value that we get when we divide the area under the purple curve by the width is 10, then that's my cruise control speed. That's what we would call the average rate of change, or in this case, that's what the average velocity was. When I was doing this purple motion that was changing all the time, speeding up, slowing down, my average velocity was just the total distance I covered, total displacement, divided by the total time, right? That's all it was. That would have been 10. Okay? Question?
So basically, if we looked at like the curve and like the straight line, they'd basically be the same amount of like velocity you're getting at the same speed.
Well, the velocities change because we're measuring velocity as a function of time, right? So this velocity, it starts off at 10, but then it gets real fast, and then it gets pretty slow. But I end up having the same area that I would have if I just chose a velocity of 10 and stuck that way the whole time.
So the 10 meters per second would basically apply to both
It
straight and
it will that's the velocity that would give me the same red area as purple area. Okay? Everybody get that? And so I could accomplish, I mean, if you want to think about this in terms of our kinematics example, it just means that I could step on the gas and step on the brake and do all that stuff, or I could just put my cruise on 10 meters per second the whole time. The result's going to be the same. After this amount of time that we're looking at from A to B, after that time interval, I would have traveled the same distance. My displacement would be the same under both. So all the mean value theorem for integrals says is if I have a function that's continuous, doesn't even have to be differentiable. It could have points on it, right? But if I have some function that's continuous everywhere, so it's defined everywhere on this domain, then I can always do this. I can always redistribute that area into a constant flat top function, and we'll call that value the average rate of change. There must be, by the mean value theorem for integrals, there has to be at least one place in the interval where I'm at my average rate of change. Doesn't that make sense? If I'm going faster than 10 at some point and slower than 10 at some point, then I must pass through 10, right? Pass through the average because the function's continuous. That's our criterion. Okay? Does that make sense? So this is stated in two ways. This is probably the most useful way is to write this in terms of an average. A bar on top of something in physics means average. So the average value of the function is just always going to be the area under the curve divided by the width of the interval. Okay, that's the average value. You could also write it this way. The area under the curve is equal to the average rate of change times the width of the interval, right? That complicated purple area, isn't that just equal to the red height times the red width, right? That's the red height, f of c. F of c, we're going to call f of c the average rate of change. What does the c have to do with it? Well, the c is the value that you're guaranteed to pass through where your instantaneous rate of change is the average rate of change, right? So really, it's weird that we would even call it f of c at this point because we haven't started looking for c yet, but we're just anticipating that we're going to, right? So we call it f of c. That means the average rate of change. See right there? F bar equals f of c, okay? So now I think it helps to do a problem. I don't know if we're going to get one in or not, but let's try one. Like, what about one like this? Okay, find the average value of f of x equals 4 minus x squared on the interval from -2 to 2. Does this meet the criteria? Is f of x continuous? Yeah, there's no place where I'm dividing by 0, right? So we're good. Check that off. It is continuous. So then if we want to find what the average value is, this is really easy, right? The average value, we'll call it f bar, is equal to the area under the curve. How would I write that as an integral? Okay, so the integral of f of x, which is 4 minus x squared, dx from -2 to 2, divided by, so the area divided by the width, right? That's all we're doing. There you go. 2 minus -2, which is 4. Okay, good. So then we could even make this simpler. That's an even function, right? So we could write that as 2 times the integral of 4 minus x squared from 0 to 2 over 4. And it's no big deal, right? So real quick, what is that? That's going to give us integral of 4 is 4x. Integral of x squared is x cubed over 3 evaluated from 0 to 2. 2 over 4 reduces to 1 over 2, right? And so if I evaluate that at 2, I'm going to get 8 minus 8/3 minus evaluated at 0. It's just 0, all divided by 2, right? Everybody see that? Okay, so that's giving me 16/3 over 2 is 8/3. So there's the value, there's the average value of the function. Now tomorrow, we're going to find the value of c, where that happens. We'll just set the original function equal to 8/3 and solve for x. Okay? Actually, tomorrow you guys have a work day. I'm gone tomorrow in the morning. So